mature enough to automatically extract parallelism, as compared to compilers like LLVM and GCC, which did a wonderful job for the CPU. So what really the programming language did is it put the power of the GPU into the hands of the programmer. So the programmer could really take the hardware, understand the possibility of what's possible in the hardware, and write tremendous performance programs. And you've seen in your assignments that you've done over the last 4 days that even simple programs like sorting, reductions, you get tremendous speed up because there's so much computing horsepower that's available in the hardware. What CUDA did is it resulted in the growth of these so-called ninja programmers who did not write software by just knowing software, but wrote software knowing hardware, right? And that really enabled these programmers to extract the last ounce of performance that's possible from the hardware. And it was a great phenomenon over the last, so 2006 was introduced, and over the last 17 years, GPU programming has really taken the world by storm. And pretty much every single walk of life, whether it be medical drug discovery, space exploration, semiconductor manufacturing, any walk of life that's impacted your lives today has really been enabled by this GPU programming, which was enabled by CUDA. So it was tremendous. However, here's where I start to digress from what Rupesh has been teaching you over the last few days. CUDA has been a programmer's nightmare, right? Fundamentally, the biggest problem with CUDA was that it broke abstractions. So computer science, since its invention in the from Turing, has really been about abstractions, where software engineers could write software, hardware engineers could design hardware. You had an instruction set, you had APIs, and you could work within your sphere of comfort, and the rest of the system would take care of extracting performance for you, and you could just write software. You don't have to deal with it. But what CUDA showed is that while they broke abstractions and were able to extract performance, it got to the point that if you broke those abstractions, and as a software engineer, you knew what the hardware details were, you could get performance, which basically was fundamentally against the ethos of software engineering, which is a big problem. Secondly, while CUDA was great, CUDA was a vendor locked-in solution. CUDA works only on NVIDIA GPU and is not portable to other GPUs, which is great for NVIDIA because it means that you can only buy GPUs from NVIDIA, but that's not great for the community at large because you want to have the ability to have to be able to program other GPUs as well. So that's a big problem. And not only was it not portable to other GPUs like AMD or Intel GPUs, the performance that NVIDIA guaranteed on subsequent versions of hardware or on subsequent versions of CUDA, there were no guarantees. They guaranteed that functionally, programs that you wrote in CUDA 1 continue to work even till date. With CUDA 12 that was released recently, the same programs that you wrote in CUDA 1 in 2007 will still work functionally. But there's no guarantees on performance. Of course, it's very difficult to guarantee performance because hardware is constantly changing, which means that every time you change hardware, you have to rewrite your program. That's not possible, right? Think about having to rewrite Microsoft Windows every time a new CPU comes out, or for every new CPU that you use in your laptops, if you have to have a new version of Windows or Linux or Mac OS, that's not possible. So this was a major problem. If there's any questions on the bridge, I'm unfortunately not able to see it on my laptop. If there's any questions somebody's putting in chat, if somebody could unmute and ask, I would really appreciate it. Okay. And you don't need to raise your hand, just unmute yourself and just ask and we can just talk. That's fine. Right. But CUDA till date is the best solution. Right? While I'm going to talk about why CUDA is difficult, why it's a programmer's nightmare, I'm going to continue to harp on the fact that it's a maintainer's nightmare. It still is the best solution. And to date, it is the best solution to extract performance from GPUs. In addition to being a programmer's nightmare, CUDA has also been a maintainer's nightmare. So in my role at KLA, and most companies, what you end up doing is you write code that lives on for several years, right? And these codes could be written by somebody, it could be deployed in the field, and then it has to be maintained by somebody else. So let's take a piece of code which is doing a kernel histogram, or one-dimensional kernel histogram, and let's walk through. I'm not able to see my mouse. So let's walk through the code, right? So this code basically has three parts. It's a typical C++ code where you first start with part A, where you initialize your shared memory counters. You go to part B, where this is actually a CUDA kernel, right? You can see it's underscore underscore global void, and you're using some shared memory with extern shared, right? You go to part B, where you go over the input case to increment the shared counter, and then part C, where you actually go ahead and increment the output with a shared counter. So it's a pretty standard, well-written piece of CUDA kernel. It's a histogram kernel. This is a real histogram kernel that is used in the wild. And let's look at what actually happens when this gets deployed. While this is where you start, as you start optimizing these kernels, again, remember, the goal of CUDA is to really extract maximum performance from the hardware. You start realizing that a lot of code, a lot of real-world code that runs on the GPU is memory bound, which means that your part A, part B, part C of the kernels are going to end up waiting on each other because there's some memory transaction that part B needs, which is not yet ready. It has to move data either from the global memory to shared memory or shared memory to registers, and so the computer is not ready. So what you actually end up doing is you restructure this code so that you hoist the memory transactions as early as possible in the kernel, and then by the time you come to the actual work, the memory transactions is completed. And on the right side, what you actually see is a real GPU fused histogram example. I challenge you to explain to me that if I gave you only the code on the right side, I challenge you that you will not be able to tell me that that's computing histogram. Because there's no beautiful separation between part A, part B, part C, as you can see on the left-hand side. Even if there were no comments on the left-hand side, I think you can kind of see it. It's pretty obvious. On the right-hand side, you have these PTX assemblies that's directly put in because that's what gives you the best performance. It's using specific number of threads that's lower than the total number of threads. There is a jump statement. It's a very complicated kernel. But to be able to extract performance from CUDA, you end up with kernels on the ones on the right side, which is the ones you actually deploy. Now, if I wrote the kernel on the right side, if I put it into the field, and 2 years later somebody reported a bug on the kernel on the right side, it is impossible for me to figure out what the code is doing functionally for me to be able to root cause the bug and fix it. So while CUDA, as you can see with GPU fused kernels on the right side, enables you to really extract really phenomenal performance from the GPU, maintaining CUDA code that's deployed in the field is really difficult because you cannot, it's impossible to understand the semantic nature of CUDA. So what are our alternatives? You've studied CUDA over the last 4 days, and I'm telling you that CUDA is a pain, right? But it is the best solution. So what are our alternatives? So there are two big alternatives that you can consider. First, let's go back to the root cause. Why was CUDA invented? CUDA was invented because compilers could not generate good code for accelerators. So let's go and fix the problem. Can we enable compilers to generate better code for accelerators? I'll give you some advancements that's happening in this field in this lecture. Second, let's go even higher, right? If the compiler is not able to solve the problem, can you improve high-level languages like C++ or Python to express parallelism better and help the compiler? These are two options if you don't want to write low-level code. So I'll talk a little bit about each of these, and I'll dive significantly deeply into C++ advancements. So let's first look at what are the options to improve code generation for GPUs. So what is the problem? Right? The problem why code generation for GPUs was bad was because traditional compilers were focusing on extracting instruction-level parallelism, which is within a set of instructions in a given loop, can you find parallelism to enable things like out-of-order execution and memory latency hiding. But that was not sufficient to be able to do code generation for vector units like SIMD or GPU units like MIMD. It was not possible. So if you look at the right side, right, you see a TensorFlow graph that what is the path that the TensorFlow graphs typically take to get lower to a CPU or a GPU or Google's accelerator called a TP. You'll see on the right side, there's something called LLVM IR, which is the primary IR that's used by many compilers today. And LLVM is the most popular compiler. But the LLVM IR is a very low-level IR. It was designed with the intention of generating code for CPUs. So with the intention of extracting instruction-level parallelism, not to extract data level parallelism that SIMD and MIMD architectures require today. There are other flows that you'll see on the right side, because there's been many efforts with many compilers to extract parallelism and target different GPUs and CPUs, but they were really limited and they were very spot-wise and they were not very successful. So today, even today, most frameworks that are generating code for GPUs, what they do is, instead of code generation to the GPUs directly, they have a set of hand-tuned libraries that are available from GPU vendors like NVIDIA or Intel or AMD. And the compiler tries to take your code and map them to these libraries. Like, for example, let's say you're trying to do a matrix multiply of 4096 by 4096 matrices. The library vendor might have a matrix multiply of size 256 by 256, right? So you tile your matrix multiply and you provide those as examples and invoke that library multiple times. And that library is actually written hand-tuned with CUDA. That really is the primary way in which code generation today happens for GPU if you want to extract good performance. But this problem is, of course, understood to be a significant limitation. So there's a lot of work today going on in this new domain of compiler design called multi-level IR compilers or MLIR compilers, where they're really trying to address this limitation. The idea here is, instead of directly moving to low-level IR like LLVM, there is a concept of progressive lowering, where you start from a high-level language, like say TensorFlow. On the right side, you can see you have a set of intermediate representations which increasingly reduce the amount of semantic information you have. But at the high level, like linalg and stencil or affine on the right side, you actually know that you're trying to do a matrix multiply, that you don't see nested for loops, but you actually see matrix multiply, right? And you don't do statistical assignment or low-level code, low-level IR representation like LLVM. But at a high level, you have semantic information. You don't know, for example, that you're going to be targeting a GPU, right? But you know it's going to be a parallel system. And so with semantic information, you can actually do better optimizations. There's a whole body of work, for example, called polyhedral compiler optimizations, which you can do if you have semantic information about the program, which earlier IRs could not give you. And MLIR is attempting to solve this problem by re-looking at compilers and to also design IR blocks that can be used across multiple frontends like TensorFlow or PyTorch or Python or C++. Right? So the idea here with MLIR is you do what's called progressive lowering, where you start from high-level semantic information. All the way down is LLVM IR, which is very low level and has hardware information. But you introduce a few additional levels in the middle. And in those additional levels, you have more semantic information at the top and more hardware information at the bottom, enabling you to do better code gen for accelerators like GPUs. So this is a very active piece of work. There's many companies, many startups, many academics who are working on MLIR, trying to really look at automated code generation for GPUs, trying to solve the problem with which CUDA was invented, right? But this work is active research that's still going on. But this is an option which I think is important for all of you to be aware of. The second option is to improve parallelism in high-level languages, which is the second option, if you remember, as to how to avoid writing low-level code. So I'm going to take first Python, and let's look at what's happening in Python, right? Now, Python, of course, today is the de facto standard for programming, right? Even before machine learning and deep learning became popular, Python was improving in its popularity. But with machine learning and deep learning, Python today is the de facto standard. In fact, we find it very difficult to find people who can write good C++ code because Python has become the de facto standard. But the biggest problem with Python is that Python code executes in a single thread. Let me repeat that, right? By default, all code in Python executes on a single thread on the CPU. Right? The language actually does support parallelism, but once you start doing that, Python code looks like C++. Data engineers, AI engineers, ML engineers don't want to write code like that. So they actually resort to writing code which is very poor performance. And without improvements to the language, the compiler is just not able to extract performance from these high-level languages. So Python has also been going through a lot of revolution over the last few years to improve the expression of parallelism. Right? Some of these examples include things like domain-specific languages or DSLs, like TensorFlow or PyTorch, right? So these enable the programmer to use operators which tell the compiler, okay, this is a matrix multiply, and therefore when you lower the matrix multiply or compile the matrix multiply, you can generate code that can run on the GPU, right? These domain-specific languages give operators and enable Python code to become parallelizable a lot easier. Second, there's a whole body of work called with around Numba, which enables JIT compilers for Python, which actually enables you to extract performance a lot better. It's a lot of work going on there. There is also active work in the form of things like PyCUDA and OpenAI Triton, through which you can actually write GPU kernels in Python directly, right? So GPU kernels, you can actually write them in Python. All the assignments that we've given in this course, of course, make you write GPU kernels in C++, but through PyCUDA and OpenAI Triton is not the same as CUDA. The kernel looks a little bit different, but you can actually write GPU kernels in Python through OpenAI Triton and PyCUDA. I encourage you to play with both of these in your Python programs to see what kind of performance you get. Lastly, there's languages like Mojo that attempt the same thing. Sorry, there's a typo, I'll fix it. But there's new languages that are coming up like Mojo, which are trying to take a superset of Python and enable you to express parallelism from the ground up. Right? What this means is that in Mojo, you're writing Python code, but you can also express parallelism. You can write GPU kernels in Python and so on. So this limitation of Python, where it needs a better way to express parallelism, has been identified, and that's been addressed. We next turn to C++, which is, of course, my favorite language, which is the language that we've been talking about here for the last 4 days. And C++ has also been going through a revolution. Right? Over the last 10 to 12 years since the start of C++ 11, which is now called as modern C++. All these variants of C++ are called modern C++. You'll see that there's been an increasing amount of focus on enabling parallelism better. C++ 11 introduced threads, mutexes, locks that gave you better expression of parallelism. So the old way of expressing p threads in C got abstracted away, and you could write threads and mutexes and locks, which makes your code a lot easier to parallelize and to express the parallelism. C++ 17 brought out parallel STLs, a phenomenal revolution where you can write STL code and you can express parallelism in them. We'll talk about some of those advancements here. And with C++ 23, you're seeing even more parallelism being embedded into C++ through things like stood future extensions, data parallel vector libraries, and so on. So there's also a lot of work going on at the language level to try and improve parallelism. C++ 26 is also looking at a lot of these advancements and so on. So what really is the impact of these advancements? Right? So let's take a piece of code. On the left side, there's a piece of code that's written in C++ with OpenMP, right? This is actually production code that is used for a particular CFD kernel that is deployed in the field, right? And you can actually see that it looks like typical OpenMP parallelized C++ code, right? There's a bunch of for loops, bunch of if constructs, there's pragmas to say which one goes where. The challenge here is that, this was written with traditional C++, right? You can see this typical for loops and if constructs, but getting semantic information was not possible. So now what these changes have actually done is, with these advancements in the language, it lets the programmer express what you want to do and not how you want to do it. And it puts the onus of converting the what you want to do to how on the runtime and the compiler. So on the right side, you'll actually see that you're using standard libraries called stood transform reduce. You're using lambda functions. There's a stood numeric limits that you actually see that as a max function that it gives you that you can use. There's lots of algorithms that C++ is giving you. And under the hood, these algorithms are expressed and written in ways to parallelize depending on the kind of hardware that's already available. Right? So these advancements really are making the programmer express, again, what they want to do and not how they want to do it. And leveraging these automatically gets you features of parallelism, which previously was not possible because on the left side, you really had to write OpenMP pragmas and figure out, okay, this is parallelizable, there's no dependence here, and give a lot of information to the compiler. But on the right side, those pragmas are all gone. Right? The language expressiveness has improved for you to be able to write these programs a lot easier. So one question I always ask, I always get asked when I talk about CUDA algorithms or C++ extensions, right, is, it's always cool to write complex programs that nobody can read, right? So people say, hey, you're making me a stupid programmer, right? Are we really making these programmers dumb? I dare say that's not, right? It's really trying to make you as a programmer smart, where we want you as a programmer to express what and not how, and let the compiler or the runtime figure out the how from the what. And that really is the intent of these advancements that's happening both in the compiler land and in the language. So this brings me to what I will be focusing on in this lecture. It's actually this lecture. So I will be giving you a sample of the advancements in C++ for heterogeneous programming. Right now, this is a very fast-moving field. Right, there's every day, every month, there's papers being published and so on. So you'll see that I'm just enabling you to explore the space. Right, I'm not an expert in this. I'll first talk about introduction to data parallel C++. And then we'll talk a little bit about the C++ STL algorithm library. And then finally, we'll talk about a topic called execution sequences in C++ 17 that enable you to express parallelism. Now, a lot of the content and the material here is borrowed from this textbook, which is a C++ higher performance by Angris and Victor. It's a fantastic textbook. Right? If you have access to this textbook in your libraries, I strongly encourage you to take a look at it and continue this learning journey. So before I dive into data parallel C++, I'm going to pause. If anyone has any questions, please feel free to unmute yourself and ask, and then we'll dive into data parallel C++. Okay, assuming you can all hear me, can somebody please confirm that you can still hear me?
Yeah, we can hear you.
All right, good. Thank you. That helps. Okay, let's move forward. So let's talk a little bit about data parallel C++. So DP++ is a language extension to something called SYCL in C++, introduced by Intel under this umbrella called One API, where the idea of data parallel C++ is you write DP++ source code, and using extensions to Clang and LLVM, the DP++ runtime allows you to target the same code on different hardware, whether it be CPU, GPU, FPGA, accelerators. And the GPUs that DP++ lets you target is not just Intel GPUs, but you can also target AMD GPUs and NVIDIA GPUs. And so that's the promise of DP++, which is really to write one code to really rule them all. So what is DP++? DP++ stands for data parallel C++, which is C++ with a standard called SYCL, and then a few additional extensions on top of that. SYCL is the next generation standard from the community that brought us OpenCL, where it enables you to program accelerators. And DP++ adds some extensions on top of SYCL. Now, why am I saying this? Just getting some lineage of where this came from is useful to know. This DP++ is fully built on top of modern C++. So you'll actually see, I'll show you programs, I'll walk you through some of those programs, and you'll see that the code looks just like modern C++. There's no special new type of coding that you have to learn. You just need to know C++ and use the right C++ code, and you get data parallelism automatically. It's pretty cool, actually. The SYCL standard is expected to be cross-architecture, like I mentioned. So you can run not just on different CPUs, or different hardware like CPUs, GPUs, and FPGAs. You can also run on different types of GPUs like NVIDIA, AMD, and Intel GPUs. So here's an example of a DP++ program. Okay, so you start with including this pound include cl/sycl.hpp. Let me see this.
Sir, excuse me. What is the role of Clang here?
Yeah, good question. So Clang lets you compile this code down. So what the implementers of DP++ have done is they've extended the Clang compiler. It's a C language front-end compiler for LLVM. That's Clang, right? They've extended the C language front-end compiler to be able to understand these DP++ extensions that Intel has implemented and to be able to compile with DP++. So you do NVCC to compile the CUDA code that you write, which is basically the NVIDIA extensions to Clang. Here you do DPCC, which is the DPC++ extensions to Clang, to basically to be able to compile the constructs, because DPC++ introduces a few classes and constructs that are not there by default in Clang, because the language C++ doesn't have them. So Clang is the compiler. I hope that answers your question.
Okay. Yes, okay.
Good. So let's take a look at this DPC++ program, right? So I'll just walk you through the various portions of it. Right? The first part, where inside the int main, you have a few, you have a few things. You have something called a range that you're introducing. You have something called a buffer. We'll talk about each portion of it, but think of it as the first section, right? Until you get this a.get access is actually running on the host, and then you have this h.parallel for. That is actually the device code, where you're telling with the lambda function what should the device code be, what is the kernel that you're going to execute, and then continuing past the device code, you get a result, and all that is host code. Okay. Now I'm going to pause here and ask, compared to the CUDA codes that you've written, how does this? What are the differences that you see? Please feel free to unmute and answer. Right? What are the differences that you see? Think about how you wrote CUDA code, and think about what this code looks like.
No explicit memory transfers. One is the thing.
Excellent.
Yes.
No explicit memory transfers. You have to do those CUDA mem copies and CUDA and sync, right? No explicit mem copies. Very good. What else? Let me give you a hint, right? In CUDA, is your kernel function written separately, or is it written as part of the main code?
Separate. In CUDA, it's separate.
Separate. CUDA, you write it separately, right? It's not part of the main code, right? So you write an underscore device or underscore global, and all you do in the host code is just you launch, right? Here, you'll see that you're not launching anything, right? You're just giving the device code as part of your straight line C++ code, and the compiler and the runtime take care of the launching of the GPU with the threads, etc. Right? So, as a programming paradigm, DPC++ is more intuitive for natural C++ programmers because it is really just straight line code. You're not writing separate functions. So, from a programming paradigm, it's very attractive. And so, these are the two big differences, right? There's no mem copies. There's no explicit data management that you have to deal with. The compiler and the runtime take care of it, and it's just straight line C++ code. There's no separate functions that are dealing with the. There's no separate functions that you have to write. Okay.
Then how can we know which variable declared in GPU memory and these are declared in host CPU memory?
It's a good question, right? The problem is that question is making you think as a software programmer, right? You're thinking, what is device code? What is memory? What is GPU memory? What is CPU memory? We don't want to think about that, right? As a programmer, I want to think about variables, right? I want to think about, for example, here there's an a.get access that gets you access to something called edge, right? Which is a handler, right? You got access to something and you pass that to the parallel for, right? And you got the result of that from a.get access read. Auto result equals a.get access read. So you are only, as a programmer, dealing with data dependencies. You are not worried about how this data moves from CPU to GPU. You are saying that the h.parallel for has to run on the GPU, right? It needs to take the data from the CPU to the GPU, and the data has to come back to CPU. But how it does it, when it does it, as a programmer, you don't care, and you shouldn't have to care. We'll talk about how data actually is transferred in the coming slides.
Okay, thanks.
Any other questions? So this is a little bit different, right? So the code looks a little bit different from CUDA. So it's a little bit of a learning curve. But once you understand and appreciate how the programming language looks, you actually start to see the simplicity of it. It's actually a beautiful programming language. Okay. So let's talk a little bit about the constructs of DPC++ that are used in this particular program. First, on the right side, you see something called a queue. There's a queue.submit, right? The queue is essentially a construct that lets you target a device. Okay, so for the queue, you've told the queue that you want to submit and you want to get a handler, right? So the queue is actually a queue that says, I want to run some code that's inside the parentheses defined after the queue on the device. And that queue is associated with a specific device. We'll talk a little bit more about queues in the coming slide. There's something called a buffer. Right? A buffer actually enables you to share data between devices. And the buffer construct is what tells the runtime that this buffer is going to be sent to the GPU and the CPU. For example, on the right side, you'll see you declared a buffer called A around a variable called R, which is a range. Right? Now that buffer is the same buffer that you use inside the device code where you did a.getAccess with write, and is the same buffer that you use outside the device code and the host code at the bottom, which is auto result equals a.getAccess read. So the buffer actually enables you to share data between CPU and GPU, and the runtime takes care of moving the data, that is the buffer, between CPU and GPU automatically. Third, you'll see this parallel for. Right? So the parallel for is an example class of a kernel. There are other types of kernels that you can write where you want to run a single thread or you want to do a parallel work group. There are ways to create kernels, but this is a special construct, which is an extension to C++, which tells the runtime that this is the actual kernel to run on the device. And the number of threads that have to be used in the parallel for are dictated by this range concept that's declared on the top, and that's the way you do it. And all of these, the queues, buffers, and parallel for, are all extensions to C++, and they have been added as libraries to C++. So compliant C++ compiler, which is like the Clang and LLVM, which is extended with TP++, can actually compile and run this code. Okay. So going back down to the GPU and looking at how kernels actually execute, much like CUDA, DP++ also has a notion of a grid, a thread block, a warp, and a thread, but it's just called slightly differently in DP++ terminology. What used to be called a grid in CUDA is called an ND range, where an ND range can be an n-dimensional block. In this case, we're showing a 3-dimensional block, and an ND range defines the total amount of work that's to be done, which is again similar to grid, right? An ND range is composed of what's called work groups, which is like the thread block that you actually have in CUDA. You compose thread blocks to form an ND range. Each thread block's dimension is called a each work group's dimension is called a subgroup, which is like a warp, right? So multiple subgroups execute in parallel in the hardware. Now you'll see that your subgroup is actually not exactly a warp, okay? Now in CUDA, because you wanted the programmer or the CUDA designers wanted the programmers to know the details of the hardware, they explicitly clarified that this is the size of a warp. But in DP++, as the language was designed, they didn't want to tie it because they didn't want the programmer to know that this is 32 threads that's going to run in parallel. So there's a notion of a subgroup. The implementation of the hardware can run all threads in a subgroup together or not in lockstep. But as a programmer, you should not have to worry about it. That's the idea. And finally, going down to the last thread, which is called a work item, you execute a single instruction or you execute a piece of work in a work item. And that work item is part of a subgroup. That subgroup is part of a work group. And that work group is part of an ND range. The total work is defined by a product of all of this. Again, this is exact terminology that you also use, a similar terminology that's also used for CUDA with grid, thread block, warp, and thread. Here you use ND range, work group, subgroup, and work item. Okay, that's the idea. Now let's talk a little bit about queues, because this really is the fundamental concept that enables executing these kernels on the devices. A queue is a construct that enables you to submit work to a device. Okay, so the idea is that you queue a kernel, and that you add a kernel to a queue, and that queue is associated with a particular device. And once you add a kernel to the queue, the runtime takes care of executing that particular kernel on the device. Each queue targets one device, but there may be multiple queues targeting the same device. And when you have multiple queues targeting the same device, the order in which the work items that are queued into Q2 in this example and Q3, there's no relative ordering between them. The only ordering between them is data flow. The program or the compiler or the runtime guarantees that data flow in the program is maintained, but between Q2 and Q3, the order is not determined otherwise. And again, from a programmer's perspective, you only should be thinking about data flow. I have an example to clarify this. So this particular concept of data flow will become a little bit clearer in the next slide. Okay. Now you can try. Sorry, was there a question?
Yes, sir. Sorry for interruption, sir.
No, not a problem. Please interrupt.
Sir, you have told this buffer right in DPC++. So is it similar to hostolog in CUDA? Because I think in CUDA the memory is internally allocated separately in both CPU and GPU. I'm not sure whether it is true, but I think is it like explicitly it is shared among CPU or GPU, or internally it is allocated on CPU and it is allocated on GPU, or we should not worry about that?
You should, from a DPC++ perspective, you shouldn't worry about it. So buffer is a construct that lets you share some pre-allocated memory, right? So hold that question about buffers. I have a section that talks a little bit more in detail about buffers. And if after that it's still not clear, you can then dive a little bit deeper. Okay.
Yes, sir. Sir, if we see the code which you have shown in the previous slide, that so there is a device code, right? So
yes,
just out of excitement in the CUDA, like if you launch a kernel, the CPU will not wait; it will go on. Like, is it the case here?
yes, it is the case here. You actually come to you in this case once the q h.parallel for inside the q.submit executes, the CPU code will come immediately to auto result. But because you have a auto result is a.getAccess, and inside the q.submit, the parallel for is writing the same buffer. A.getAccess write, right? You're actually writing the same buffer inside the parallel for, and outside the kernel in auto result a.getAccess, you're reading. There is a data flow dependence between the writer, which is the kernel, and the host code, which is the reader, right? So the runtime makes sure that's the synchronization. So you don't need a sync, because the host will actually wait. Because you have a buffer, the host will wait till the kernel is completed before the result getAccess actually executes. It automatically is an implicit sync order. Does that make sense?
Yes, sir. Thank you, sir. Yes, sir.
Yeah. So again, it's data flow, right? So I have the next slide on this particular data flow will clarify this question also. Okay. All right, great. So we're talking about queues, right? So the idea of a queue is you can get in your system, depending on the available hardware, you can get different types of queues. By default, you just call queue. You can get a target. You can get a queue targeting any device. Typically, you'll get the queue associated with the CPU. Now remember, right? In DPC++, you can program the CPU the same way as the GPU. So you can write a kernel that runs on the CPU, which is again a DPC++ construct. And in all you have to do in the code is you change the queue to a queue of GPU selector. The same code will run on the GPU. You get a queue of Intel FPGA selector or any other accelerator selector. The same code will run on the FPGA or accelerator. And you don't have to make any changes to the code. And that is really the power of DPC++. And that lets you run the same piece of code with very minimal changes on different hardware overall. Okay? So the queue lets you get this queue, the queue construct lets you get a handle to a queue through which you can submit jobs that can run on a GPU. Okay? Now, the kernels that you add into a queue may execute out of order based on data flow. So let's take an example and look at this particular example, right? So here is a particular example. So you're starting out with declaring a range of numbers, and then you have two buffers, A and B. So these two buffers, think of these as the way by which you're going to share data between different kernels. I've written 4 kernels here. I'll walk you through the 4 kernels. Kernel 1 in red submits jobs to a queue where the variable auto out is equal to a.getAccess is going to write A. Right? Auto out is equal to a.getAccess access mode write means you're going to write A. Then the second kernel 2, you again get A in the mode of writing. right? So you're going to write A. You're going to write some value out of IDX equals IDX of 0. So you're going to write some values into A. The third queue, what you're doing to the submit there is you're going to write, but you're going to write a different buffer B, where you're getting B.getAccess right, and you're going to write B. And then the fourth queue, the fourth submit, what you're doing is you're getting something called in, where you're getting A in read mode, you're getting B in read write mode, and then you're doing some computation where you can read A, but you can write B and read B. Okay. Now, I want to see which of these kernels can I execute in parallel and which of these kernels must execute in sequence. Please feel free to unmute yourself and talk, right? But let's just think about data flow dependency, right? You need to obey data flow in the order in which you see the program, like a regular piece of code that has variables that are written and read. So the execution order of the hardware, because you're submitting all these 4 kernels to the same queue, needs to be obeying the data flow dependencies of the hardware, of the program. So can you tell me which of these 4 kernels can I execute in parallel? Which of these must execute sequentially?
1 and 2 should be in sequential.
Okay.
1, 3 can run in parallel.
Okay.
1, 3 or 2, 3 can run in parallel. 4, I'm not sure.
4, you're not sure. Okay. Somebody wants to take a crack at 4, or if somebody thinks that he was wrong about 1, 2, and 3, somebody thinks we should run it some other way. Somebody wants to take a crack at 4. Can you run 4 in parallel with 3?
I guess no, because there is an in node B.getAccess.
Yes.
Which is data dependent on kernel 3, I guess.
Good. That's good. Can you run 4 in parallel with 2?
Yes, sir.
No. I guess no, because I think the same reason the kernel 2 is dealing with A and kernel 4 is also dealing with A and write read is happening.
Exactly, right? So kernel 2 is writing A and kernel 4 is reading A. So from A's perspective, kernel 4 is data dependent on kernel 2. So here is the data flow graph, right? Here is the data flow graph that's showing dependencies. Kernel 1 executes, kernel 2 must execute after kernel 1 because you're writing A again. So you cannot start writing A until the first set of writes are completed. There's a data dependence. Kernel 3 is dealing with B and is not touching A. Therefore, kernel 3 can execute in parallel with kernel 1 and kernel 2. There's no problem. Kernel 4 is reading A, reading B, and writing B. That's why there's an in-out access or read-write access for B. Therefore, kernel 4 must run after kernel 2 and kernel 3 are completed. Now, the beauty with DPC++ is you don't have to worry about queuing, synchronizing at all. Because of the fact that you have these buffers and you're only reading and writing data through these buffers, the synchronization between kernel 1, 2, 3, 4 execution is automatically taken care of. And the order in which the kernels will execute in hardware will be the same order as what's shown on the right side. Kernel 1 will run, kernel 3 will run in parallel, kernel 2 will run in parallel with 3, but only after kernel 1 is completed. And when both are completed, kernel 4 will be launched. But from a programmer's perspective, there's no launch code, there's no synchronization, there's no data copies.
So,
Yeah, go ahead.
suppose this write and read write is everything is replaced with only read, and is everything is parallel or is it again in queue fashion?
No, everything is a read, everything can be run in parallel. There's no dependency.
Okay,
right? It's only a read after read is not a hazard. Right? Only write after read or write after write is a hazard. So say if everything is just read, everything can run in parallel. But from a programmer's perspective, you only are worrying about data flow. You're only thinking about A and B. The kernels are a consequence of the data flow. The order of executions of the kernel is a consequence of data flow. And you as a programmer don't have to worry about it. You have to think about data flow. Okay. Any other questions on this? Anybody starting to like this more than CUDA? You don't have to do mem copies, there's no synchronizations. Sorry, was there a question?
Can you please explain that A out, auto in, last auto in out? Can you please
In
explain
out,
that
yeah.
little bit?
Sure. So there are three modes to get access to buffers, which I think I talk about next. Yeah, I talk about next, right? But I'll talk about next, but I can explain this to you just so you're aware. So here what's happening is the auto in out in kernel 4, right? For B, you can either get a buffer in read mode, in write mode, or in read write mode. If you look at the last line of code, in out of IDX star equals in of IDX. That is basically in out of IDX equals in of IDX into, sorry, in out of IDX equals in out of IDX into in of IDX, right? Because star equals is a multiply and assignment operator. So you're reading in out, therefore you need B in a read mode, and you're writing in out, therefore you need B in a write mode. So you get this accessor called read write. Make sense? Is that clear?
Yes. Okay. Yes. Yes.
Good. So buffers, as you've seen in the previous example, is really the mode by which you express parallelism and you express data sharing between different constructs that's going to execute on different pieces of hardware. Buffer is an encapsulator for data in the SQL application, as you saw over here. Accessor enables you to access a buffer. So when it said on the right side, where we said out equals a.get access of a particular mode, what you got as out, or in the previous example, what you got as in out or in, are called accessors. These accessors let you specify a particular mode to access the buffer. And with those accessors, you can write your kernels. You'll see on the right side, the parallel for uses the accessor out, like a regular variable, like a regular array, right? And on the bottom, after that in the host code, you'll see auto result equals a.get access. That's an accessor, and you can access the elements of the buffer B using the accessor, right? And those accessors, once you've defined the accessors in a particular mode, what this is telling you in this particular code is first the buffer A, because A is what's storing the data. Accessor is just giving you access. Think of it like a pointer, right? It tells the runtime that A as a buffer first is going to be read or written. So it's going to be written from the GPU, right? Because you're submitting it to a queue and you're taking it in mode write. Once it's written on the GPU, there is going to be a read of that same buffer back on the CPU, because the result is going to do a.get access in read mode, and that read is going to run on the CPU, right? Now, what this means is you need to be able to first read A from the GPU, assuming that the queue is targeting a GPU. Then you need to be able to read A from the CPU, because you're going to do a stood out. So both of those have to be available. So the runtime takes care of moving the data between CPU and GPU. The buffer A is automatically moved between CPU and GPU because of these accessors and the modes in which you've given it, right? In fact, the runtime here will be smart enough to realize on the right side that the first access to A, you declare the buffer A on the CPU, the first two lines of code, you've declared the buffer A on the CPU, but you've not written any values, right? The first time you actually write values is on the GPU. So what the runtime will actually do here is it will not create a buffer on the CPU, copy it to GPU and bring it back. Instead, it will just create a buffer on the GPU when you do the write and bring it back to CPU when you want to do a read. And that's all it will do, right? So again, expressing what you want to do and not how you want to do it allows the program to really extract parallelism automatically, right? Like I said, the presence of the buffer is dependent on the accelerator. The compiler and the runtime handles data placement and movement, and the kernel execution and the data movement is completely handled by the runtime. You as a programmer does not have to worry about data movement. You as a programmer has to think only about data flow. So the person who had questions about that write and read write and in out, hopefully this makes it clear, right? What you actually are doing is you're not taking the buffer, but you're taking what's called an accessor to the buffer, and that takes care of it automatically. Sorry, this is not the two buffers, and that takes care of it automatically. Yeah. Okay. Any questions to accessors and buffers? Okay, so the next concept is a fairly simple concept where this is asynchronous execution. I spoke about this already, where the host code and the kernel execute in parallel. Synchronization can be done through syncops, but that's not required because if you actually do accessors and buffers, your synchronization is automatically taken care of. You already DPC++ also has a concept of synchronization operators like you have in CUDA, but you don't need to use it if you're using accessors and buffers. So in this case, once the q.submit completes, the host code will submit the kernel and control will return. Other execution on the CPU that's not dependent on data generated from the kernel submitted can actually continue. And the execution on the CPU will stall once you need data that has to be generated from the kernels that you submitted. And once those kernels are completed and that accessor returns, only then can the execution on the CPU continue. And so again, data flow, it's taken care of automatically from data flow. Okay, good. Now, buffers and accessors are the default mechanism of abstraction for DPC++, and it's only available from a particular version of SYCL. However, programmers are used to unified shared memory, right? Where we've written programs for a long time, creating with malloc, dlloc, free, using pointers. And these buffers and accessors are a new method of accessing memory. So what the DPC++ team realized, and this is one of the key differences between DPC++ and SYCL, where SYCL said, sorry, can't do anything. You either write buffers or you're not writing SYCL code. And so it made it very difficult for programmers to access SYCL. It was a very strong learning curve. So what DPC++ said is, okay, we understand that buffers are hard. So we'll provide this extension called unified shared memory, which will make your code look a lot like traditional C++ code. And this is an alternative for memory management. For example, take a look at this code, right? Here on the top, the auto A equals malloc shared is a way, is a overloaded operator on top of malloc with unified shared memory, where you're actually allocating memory that is declared to be shared between devices because you've used this notion of malloc shared. There are a few other extensions that tell you if this malloc is going to be host only, device only, or shared between them. But once you do that, you'll see the code inside your parallel for resembling more of a traditional pointer like access. A of I star equals B of I. Right? And you're not really doing, here you're not really doing read-write access and things like that. Right? So once you did malloc shared, it said that this data is going to be shared between CPU and GPU. And you can access it both inside on the CPU and in the GPU. Here in this example, you're accessing it inside the GPU kernel and it's expected to work. Now, the main thing that DPC++ said is it's not expected to give you peak performance automatically. The idea with giving USM is that traditional code that you've written with malloc could be easily migrated. Right? You could convert it directly to DPC++ code, but if you want to get performance, you really have to use buffers and accessors. So let's talk a little bit more about malloc shared before I come to any questions. So just hold your questions if you have any examples. So the three types of allocations. One is called a malloc device, where you're saying, I want to allocate on the device. This, if you do that, the code is not accessible by the host because it's allocated on the device. And you specify which device. So it's accessible only on that device. Other devices being able to access it, it depends on implementation. And that code, that memory that you allocated cannot be migrated to the host device or any other devices. On the other hand, you can do malloc host, which says I'm allocating on the host memory, right? And any device can access it, but it's going to be inefficient because it's going to remain on the CPU and you just make a copy or you just get particular elements in out. The third type of allocation is called a malloc shared, where you're saying I'll start with allocation on the host, but I know that this device, this buffer is going to be accessed by both host and device. So it's accessible to both the host and device. But if your execution requires it to stay on the device for a long time, the data may actually migrate from host to device based on performance constraints. And as a programmer, you don't have to care about it. Correctness is always guaranteed based on data flow, right? As you can see, the host device and malloc device and malloc host is forcing you to think a little bit about where the data should be and data movement between CPU and GPU. Malloc shared gives up a little bit of that control and tells the runtime, okay, you take care of it, you migrate it to where you think it's required for performance. But if you move to buffers and accessors, none of this is required. You declare a buffer, you get an accessor, you say, okay, I'm going to use this accessor in a particular way, and the code automatically moves. So what I'm going to do next, and then I'll take questions, is I'm going to give you an example of a particular piece of code that is written with USM, and then the same piece of code that's written with buffers. So that will make this example a little bit clear, right? So here's an example where you have three variables, A, B, and C. They are declared as malloc shared. You malloc shared a particular array of size n, right? Then you go through a for loop. A of I equals I and B of I equals 2I. Then there's a q.submit where you are submitting to a particular queue. Let's assume that the queue is on the GPU. I'm not showing you what kind of queue you're getting. Let's assume it's a different device. And you do a parallel for where you access C, A, and B. Right? You'll see at the end of q.submit, because you're not using buffers and accessors, you have to explicitly do a q.wait. It's a synchronization operation because it's pointers. The compiler cannot figure out disambiguation, so it cannot figure out what data flow happens. So you have to explicitly have a q.wait. Okay. At the end of q.wait, A, B, C are updated and ready to use. So walking through this, you declare the array, you initialize the array, you rewrite the arrays inside the queue, and the USM arrays are updated because you had a q.wait. All right. Here's a question. Can we use malloc device instead of malloc shared? Yes. How many of you say you can use malloc device instead of malloc shared? Or how many of you say you can't? Or if you can't, why not?
We cannot use malloc device because we are accessing both A and B pointers inside the CPU for loop.
Yeah, so the for loop on
So
top
it needs
is
to
running
be
on the
on
CPU. Exactly. So the for loop running on top is actually running on CPU. The for loop, the parallel for on the kernel is running on some device. And so you cannot do malloc device. That's good because the host cannot. Can you do malloc host? So if you do malloc host, the for loop on top obviously can access it. Can the parallel for inside the q.submit access the same buffer if you do a malloc host? Yes, no? The answer is yes. Sorry, can you say that again? Your voice was a little choppy. Okay, so the answer is actually yes, because based on the previous table, exactly, you can access it. But the problem may be that the performance might not be optimal because you've done malloc host. The A will remain on the host always, right? So it may actually do a read from the host. It may not move the entire buffer from the CPU to the GPU. Right? It might read particular elements as you're reading them. So performance could be suboptimal. I encourage you to write this particular USM example on the Intel Dev Cloud and see what kind of performance you get between malloc host and malloc shell. It's a very simple example to actually play with this. The same code, if I turn to buffers, here's how the code will look, right? So you've done A, B, and C. Again, here, instead of doing any kind of malloc shared, malloc host, you're just doing malloc, right? You're just allocating the memory. You access it on the CPU. Again, use a simple for loop. Now, because you're going to go into kernels, you need to create a buffer with it. The buffer is just a wrapper. And so you've created this buffer called AB, BB, and CB, which is basically a wrapper given a particular range, which is the number of kernels you want to run. And you got a buffer wrapped around A, B, and C. Now, to run inside the parallel for, you're getting accessors, and you're telling that accessor AA is getting AB in read mode, accessor B, AB is getting BB in read mode, accessor C, AC is getting CB in write mode. And then you write the parallel for. Now, the beauty of doing this is that the data movement between CPU and GPU is taken care of by the code. And once the q.submit returns, and when you try to access AC, that data flow dependency will automatically take care of stalling until the q.submit is completed. So there's no need to write any q.wait over here. Again, so initialize the arrays, create the buffer, create the accessors. use the accessors in the kernel, and when you're out of this, your C++ arrays are automatically updated. Any questions?
Sir, in the previous slide, you have told that you have to explicitly wait. So,
Yes.
suppose if we don't have wait and instead we are trying to access the memory directly, which we did in the earlier slides. So,
Yes.
will the DPC++ ensure that the data flow is maintained? Because
No, it cannot. With USM, it cannot maintain because it cannot know, right? It cannot know. It doesn't know. You've not given control of the buffer to DPC++. DPC++ gets control of your buffer only with an accessor. If you're not given an accessor, it is going to be safe and say, I don't know what you're doing with it. I cannot guarantee. Please do a q.wait if you want to guarantee results. And it won't even complain. Probably, I think newer versions of the DPC++ compiler might complain if it has advanced disambiguation features, but you cannot assume that it will complain also. So this kind of, again, this is the problem with parallel programs, right? Your synchronization has to be explicit. But with constructs like accessors, that is completely eliminated. That's the advantage. I hope that answers your question.
yes, sir.
Any other questions? Okay, wonderful. Actually, this brings us to the end of the DP++ section. Right? I'm going to jump to the C++ STL algorithms, but I think it's a good time for a break. So it's 11:26 in my clock. So we're going to resume after a 10-minute break. Please come back by 11:30. No, sorry, it's 10:26. Please come back by 10:35. Right, 10-minute break, 9 minutes to be precise, and we'll resume over. Okay. Thank you. See you back in 10 minutes. Okay, it's 10:35. I think we can resume. Can somebody confirm that they can hear me?
Yes, sir.
All right. All right. So hopefully that was an interesting exposure to DPC++ as a new programming alternative to CUDA, right? Which actually lets you write. We still are writing low-level kernels, except that you are writing kernels that is, targeting generic hardware, writing in C++ style, and not dealing with memcopies and synchronizations, but only dealing with data flow. What we're going to talk about in the next section for the next 45 minutes to an hour is abstracting this even higher, right? We're going to talk about the extensions to the C++ STL algorithm library that have happened that enable you to really take building blocks, small building blocks, and put together what we think will be a remarkable program. But you don't have to worry about the details inside the building blocks, but you can focus on, again, what you want to do and not how you want to do it. I've used a picture of a KLA tool to demonstrate this, which again is something that my company puts together, where we don't manufacture all the components of the tool, we assemble the tool together. Right? But assembly itself is a hard problem, but the details of what each component of the tool is actually doing is left to the tool manufacturer and enabling us to really assemble what we think are remarkable tools. So let's look at what the C++ algorithm library enables. I'm going back to the same example that I'd shown you earlier, enabling you, demonstrating that by leveraging concepts in the C++ algorithm library, you can express what you want to do. Your code footprint becomes significantly smaller, and it enables the compiler to actually extract parallelism automatically, and you don't have to worry as a programmer on how to do it. The C++ algorithm library has been available since C++ 11. It's very easy to use it. You just do a pound include library. Actually, while it's available from C++ 11, even for C++ 98, the popularity of the algorithm library was so much that the compilers that supported older versions like C++ 98 also started supporting algorithms on older implementations. There are several hundreds of functions, right? And I'll give you a perspective of how to attack the various functions. There are many built-in implementations of commonly used functions like search, sort, count, set operations, all kinds of operations. We'll talk a little bit about that. It fundamentally assumes that you use STLs, right? And it works on iterators. The main thing with this STL algorithms is that the algorithm writers did not want to deal with memory allocation. Therefore, it expects all algorithms written in the C++ STL algorithm, barring maybe one, expects you to provide pre-allocated STLs, and the STL algorithms do not change the size of the allocation. They just work on pre-allocated STLs. So if it has to fill in a new buffer, you need to allocate the buffer and give it to that STL algorithm, and it will fill the buffer based on certain constraints. So I'm sure many of you have used STL algorithms in the past. Maybe you can unmute and tell me what are some of the STL algorithms that you've used, if you've used them in your C++ programming. Has anybody used it? If so, can you maybe tell me what are some STL algorithms that you've used? Anybody who's used STL algorithms at all?
Sort is one function, like
Sort
lower bound, upper bound, lower bound, upper bound.
Very good.
And like
Anybody
binary search
else has
also
used binary search? Very good. That's a very powerful function in the STL algorithm library for sure. Anybody who's used any set operators, min, max, union find and things like that?
Yes, set it's set operations.
Set off, right? That's a good operator that's actually used. So the STL algorithm library is actually very vast. It has hundreds of algorithms, right? So as I was preparing the material for this class, I was looking at a way to simplify this algorithm, the class of algorithms. And I found this particular talk by Jonathan Bukhara in, I think it's a few years old now. I'm sure there's an updated talk, but he had a very beautiful classification of the various STL algorithms, right? In fact, he talks about 105 STL algorithms in an hour. So he actually goes through a lot of them, but because of the categorization that he provides, it actually lets you consume these STL algorithms without really worrying about every single one of them. Of course, there's always available help online through which you can see the exact syntax, etc. But he divides this entire realm he puts it on a global map, and he calls it, on the left side, there's a land of the queries. This is all the STL algorithms that enable you to do value queries, property queries, range-based property queries. On the bottom left is what he calls the land of permutations, where you can permute different arrays, permute different STLs, and so on. On the top is all your algorithms on sets, whether it be union find, set off, intersection, union, all the algorithms that are really implemented there. Right in the center is dealing with raw memory, where you want to initialize raw memory, you want to clear memory, you want to reset memory. In the middle are the structure changes. These are the few STL algorithms that actually change your STLs. He talks about those as well. Moving towards the right, you have the value modifiers, where you can replace, where you can fill, where you can generate, and so on. And all the way on the right side, there's the territory of the movers, where you can do a backward movement, copy backward, and so on and so forth. So again, I'm not going to try and recreate this entire talk. It's a beautiful talk. It's a 1-hour talk. I strongly encourage you all to just see it once. Again, you will not remember all the algorithms. 105 algorithms in an hour is a lot of algorithms, but it gives you a flavor of how to think about algorithms. And when you're working on some C++ language, on some code in C++, and you want to look at algorithms, this will help you jog your memory. So I pulled in a few examples in each category, which I already have mentioned. The permutations on the bottom left, these are the heap, sorting, partitioning, permutation operations. The value queries on the left side, again, on the top left in the map, these are your value-based algorithms that do count or do accumulate, that help you do properties. All of, any of, none of, is any of this found? Do simple searches. You can specify I want to do binary search. You can specify I want to do insertion search. Or you can just say search and it will figure out the right way to do the search. There's a lot of algorithms on sets, like I said, set difference, set union, set intersection, so on and so forth. There are the movers, enabling you to copy, move, swap ranges. Value modifiers in the middle, iota, which is one of the most useful functions when you want to initialize a particular array that you've just declared. You want to fill something, you want to generate, you want to replace. There's a structure changes, doing your removes and your uniques. And on the right side, working with raw memory, where you can do an uninitialized fill, uninitialized copy, so on and so forth. In addition, there's also a few algorithms that STL provides you that don't really fit here, which is what it fits inside this area on the bottom left side called secret runes. Talks about for each, transform operations, and so on. So the beauty with these algorithms is that these algorithms are managed by the compiler, and there's a very strict protocol on what algorithm implementations are accepted by each compiler. LLVM, GCC will have their own implementations, but the standard dictates that you need to follow certain safety properties. There needs to be certain types of testing that is done, and the compiler owners are very stringent to accept new implementations only if and only that code is stable and it gives you the best performance. So the beauty with some of these STL algorithms is that these algorithms are so implemented that if your CPU that you're going to run on has multiple threads, it has SIMD, which is AVX2, MMX, AVX512, the implementation automatically leverages the best class of the hardware that's available, the best properties of the hardware, to give you the fastest implementation that it can find. So as a programmer, you don't have to worry that you have to write vectorized code, right? The algorithm implementer automatically takes care of it. That's really the power of STL algorithms. So whether it be straight line code or it be parallelism, STL algorithms really gives you the best performance that you can have. So I strongly encourage you, if you've not used it, to really leverage STL algorithms heavily, right? For me, this was revolutionary because once I started using algorithms, I didn't have to write a lot of code. Again, going back to this example is a beautiful example, right? Which shows you on the left side, it's the kind of code that you write, right? You write for index I equals 0, I less than length, I plus plus. You're doing some indexing, you're doing some searching. It becomes so much simpler on the right side, right? You have a simple way to do max, absolute. You actually are doing all of that manually on the left side. By leveraging STL algorithms, you become so much more effective as a programmer. It's a learning curve, admittedly, but once you get used to doing it, you can actually write much more efficient, much better code than what you could do earlier. So again, I'm not going to repeat the entire 1 hour lecture. It's a beautiful lecture. I strongly encourage you to go and see it. The link will be there in the slides. And you can learn a lot from it. If there's any specific questions on STL algorithms, I'm happy to take them now. Otherwise, I'm going to move towards an extension of STL algorithms that enables you to do GPU programming with STLs. And that will really be the focus of what I talk on next. Any questions on STL algorithms? No? Okay, sounds good. So what we'll talk about next is an extension to STL algorithms called execution policies, right? So what this lets you do is it enables you to automatically select the device on which a particular algorithm will run by just providing an additional parameter to the STL algorithm. On the right side is an example where the stud transform, which enables you to do a transform of a particular STL that you provide to the stud transform library through the first parameter. In this just called par, right? And we'll talk about what that first parameter called. That's called the execution policy. You can either execute it on the CPU or on the GPU without having to change any code. And the theme of this entire talk is how do you automatically express parallelism and program accelerators? You're not even writing DP++ now. You're writing just C++, right? And by just adding a new parameter to these algorithms, you can automatically get these benefits. Okay, so let's talk about execution policies. This is what execution policies really enable. The idea is that you can specify if an algorithm can be vectorized or parallelized in the first parameter of the execution policy. Can somebody tell me what is the difference between vector execution and parallel execution? Please unmute yourself, and anybody can tell me what's the difference between vector and parallel execution? Or let's put it this way, right? So you've heard of these SIMD or vector units on the CPU. And you have GPUs that's also doing parallel execution, right? What is the difference between them? Are they similar or are they different? If they're different, what's the difference? So the main difference is that in vector units, all the units are going to execute the same instruction. So it's single instruction, multiple data. You're going to be operating on different data. In parallel execution, you do multiple instructions and multiple data. So eventually you may run the same work, but at any given clock cycle, different threads could be executing different instructions. However, in the GPU implementation in NVIDIA, you have these warps that are effectively SIMD, but across warps, you are MIMD or multiple instruction, multiple data. And in execution policy, you can actually tell that, okay, you know what, I want to do parallel execution and it takes care of it. Again, it's specified as the first parameter to the algorithm, right? And that's all you do. In the algorithm, that's really all you do. The allocation, data movement, synchronization, it's all handled by compiler and runtime. For example, let's take this example where you have a stud sort. You have an employees.begin and employees.end. You give it the begin and end iterators. And you have a function based on which you want to do the sorting. If you want to execute this in parallel, all you have to do is, if you know as a programmer that the sorting, there is going to be no data dependency between the elements that are being sorted, that are being operated on. There's no data dependency because the compare by last name is just going to do a comparison. So you're not modifying anything. There's no order dependency. If you as a programmer can dictate that, can decide that, you can tell the compiler that, you know what, this particular operation is parallelizable. Right? There's no risk in parallelism. This may not be the same case, for example, if you're doing a reduction, and if it's a non-commutative reduction, you cannot do this. But in sort, there's no risk because you're not doing any change. So you tell the algorithm that, you know, if your runtime has the ability to parallelize it, go ahead and parallelize it. If your runtime does not have the ability to parallelize it, maybe you have a single core CPU, then don't parallelize it. But from an algorithm perspective, I believe that this particular algorithm can be parallelized. So if you have an implementation, go ahead and use it. That's it. Right? It's as simple as this. It really looks stupid and dumb. It really is as stupid and dumb. And it gives fantastic performance. So there are 4 execution policies that we'll talk about. First execution policy is stud execution sequential, where you're saying the order in which I've given you the iterators and the array is the only order in which you can operate it, because there's some sequential dependence which I need to be preserved. So you cannot do any parallelism. The next which is available from C++20, where you can say, okay, there is some SIMD parallelism that's allowed, but you cannot do MIMD parallelism. For whatever reason, as a programmer, I decided that this is the way. So if you have a vector unit, execute on the vector unit, but don't do GPU level parallelism. Third is I'm opening it out and saying you can do parallel execution. And finally, the fourth is you can do parallel and unsec, meaning that if you have vector, do vector, and if you have MIMD, do MIMD. And that automatically is taken care of by the runtime. Right? Again, from a CPU program, from a programmer perspective, you're not doing much, right? You're really just writing the STUD algorithm and letting it run on the GPU without any complication. So STUD_PAR is the extension that enables you to do this, and this parallel execution policies. Each GPU has its own implementation. Each CPU has its own implementation that's dictated by the compiler. What I've done is I've taken some examples of some of the restrictions or the guidelines that are presented with STUD_PAR on NVIDIA GPU to give you some idea on how this actually works. Again, there'll be similar implementations available in AMD GPUs that's available on the CPUs that you can look at, but this gives you some perspective. For the compilation on the NVIDIA GPUs, you just have to add a NVCC flag -STUD_PAR to the compiler, to the compilation command line, and that enables automatic parallelism on NVIDIA GPUs. And of course, your algorithms written in C++ must have execution policies that are actually used as part of the algorithm. You cannot use any __ device annotation, because remember, this is just straight line code. This is straight line host code. You cannot do this inside a device code, right? And the definition of the call sequence should be in the same file, because the way the compiler is going to analyze it is going to look at the definition of the function that you're calling that could be using the STUD_PAR, could be using the execution policies, and the call should be in the same file. If it's across different files, it's not possible, because it's possible that's in a different file. You could compile it to a different library, and then that implementation makes certain assumptions. So that's not allowed in this particular instance on NVIDIA GPUs. Right? This is an important one, where the code that is used in the parallel algorithm must be allocated to the heap to leverage GPUs. Right? Now, this is pretty obvious if you think about it, because only if you allocate it to the heap can the compiler take care of moving it to the GPU. If you allocate it on the stack, the compiler cannot move it to the GPU, because that's the way the code is owned. So your data must be allocated on the heap. If you allocate it on the stack and call the algorithm, you will not get an error, but you'll get a runtime crash, and it's impossible to debug. So these are just guidelines. STUD_PAR is still pretty nascent, right? So for example, implementations guidelines suggest that you should avoid using function pointers as parameters to parallel functions. So it's recommended that you use the function object itself and the lambda. Now the reason is function pointers are bound at runtime and not at compile time. So, but when you're compiling with STUD_PAR, you need to know, is this going to run on CPU or GPU? And you need to be able to generate code for CPU or GPU. So if, for example, you have a function pointer, you cannot look at the compiler does not have to look at the function now, right? The standard says you should be able to compile without it, so you cannot generate it. Well, just give you a simple example of how this works. Here's an example where you have a void square on top, which takes a reference parameter called x, and you return a particular value. On the bottom, we'll actually see that you're giving a reference to the particular function as the last parameter to the square all function, or to the for each function. So at the bottom, you see STUD for each. The first parameter to the for each is a STUD execution par unsec, saying that you can parallelize and vectorize. And the last parameter to that algorithm is a reference to the function that is going to be executing on this particular iterators, right? Instead of providing, but that's a function pointer. You're providing a function pointer, right? So instead of that, the recommendation is just embed it as a lambda inside the function, inside the algorithm that's actually using STUD, the par unsec. Again, the reason why I picked these particular examples is to realize that STUD_PAR has to generate code at compile time based on where you're going to be running the code. So if your STUD_PAR decides, okay, I'm going to run this on the GPU, it needs to generate all that code in that compilation. You cannot have a separate compilation in the library and then link later. It doesn't work. So STUD_PAR requires that function pointers as parameters to parallel functions is not a good idea. It says, I want to see everything, don't give me pointers. And lastly, this one I'm going to kind of ignore. I'm not going to talk about it. Random access iterators are required because your GPU threads, going back to your everything you learned in the CUDA programming, your GPU threads can run out of order. They will not run in sequence. Any thread can execute as long as there is SMs available. So the random access iterator is required for parallel programs. And lastly, stood parallel does not throw exceptions. So, which basically means that if there's something wrong in the execution, your program will crash. So you need to be careful towards taking implementations like stood parallel algorithm, but it can provide a lot of benefit, which I will show you in the coming slides. Okay. Now, stood parallel is just one example of how parallelism is being pushed in C++. Now, this slide from NVIDIA is actually showing what kind of extensions are being added to C++ to make parallel programming easier. Now, I want to reiterate, right? This is a slide from NVIDIA, who invented CUDA, right? So even the device programmers are starting to look at how to make parallel programming more approachable, more accessible. And so they are, while CUDA continues to develop and thrive and continues to be the best way to get performance, there is a lot of push in trying to make the language more programmable for parallel, right? On the left side, you can see what are the extensions that have been added to C++ 17 and 20. So a lot of stuff that's come in, right? Primarily around the synchronization, scalable synchronization libraries. There's a lot of thread synchronization and so on. C++ 23 has brought this huge thing called range-based parallel algorithms, which enable you to do a lot easier programming. And you know, as they start working on C++ 23 was released earlier this year, so they've started looking at C++ 26. There's a lot of work trying to enable expressing parallelism in C++. So in fact, to the point that C++ is starting to look a lot like Python, because you can actually write again what you intend to do and not how you intend to do it. Okay. Just to demonstrate the value of doing some of these changes, here's some real-world examples where you can see performance coming out of it. On the left side is a particular hydrodynamics mini application that was demonstrated by NVIDIA. Where they actually showed you on the first two bars is the OpenMP performance on a particular CPU, the EPIC 7742. You can see that, you know, with NVCC trying to run this, you're not getting much on the second bar, it's just 3%. But if you wrote this with standard C++, and you started leveraging NVC++ with SUDPAR on the GPU, that's on the A100 GPU, you see that you get 14x performance when you move to A100 GPU. And this is without changing a single line of code. But you're not writing CUDA. You're not writing any specific device, underscore device or anything. It is just using parallel algorithms where you said with execution policies, parallelize when you can, and you just get 14x without changing any code. Here's another example with the lattice Boltzmann simulation, again demonstrated by NVIDIA, for the same ISO C++ code, moving from CPU to GPU. For the same code, I want to reiterate, it's same code, no additional work to write any new code. You get 12x performance moving from a dual socket Xeon on the CPU to a PCIe-based A100. The third one is similar example with multi-physics aerodynamic simulation. You can see with the same code between ISO C++, moving from the EPIC CPUs to the A100, you get 8 to 10x performance speed up. Now, to the point that there's even some work, you can look at the reference later, there's even to the point that for some work, the performance is pushing close to hand-tuned CUDA for some loads, right? So this is, while the Ninja programmers like yourselves continue to push CUDA performance and extract performance, there's a big body of work going on from the C++ community to enable extracting performance. And what the Ninja programmers are actually doing is they are contributing their optimized code to the libraries. Right? STL libraries are getting these Ninja programmers, giving them optimized code, and that enables getting much better performance. Okay. Any questions on STUDPAR or STL algorithms or libraries from anybody? Please. I'm just going to take a pause, take a chance to unmute yourself and ask the question. Okay, if there's no other questions, it pretty much brings me to the end of my lecture today. Right. So in this lecture, what we learned where I first spoke a lot about DPC++, where there's a big development to alternate ways to program GPUs. DPC++ targets not just Intel GPUs, but can also run on NVIDIA and AMD GPUs and other type of devices as well. And the idea with DPC++ is that it provides abstractions to hide the real hardware from programmer and have the programmer focus on data flow and not on synchronization and memory movement. We also spoke about how new ISO C++ constructs enable you to express what you're doing and not how you're doing it. STUD algorithms, STUD's execution policies are powerful tools to let you simplify and accelerate your program. And for some cases, it's even reaching the limits of what your hand-tuned CUDA is able to achieve. Finally, there's a big revolution going on with C++ to embrace parallelism. Right? Since C++ 17, there's several new features that have been added to enable you to express parallelism better. Again, to the point that it's reaching this performance that CUDA is able to reach with hand-tuned kernels. So I strongly encourage you, as you write C++ code, to look at STUD algorithms, look at STUD execution policies, and leverage it to make your performance better. Now, again, because these are still under development, to date, writing CUDA code is the best way to get performance. So what you've learned over the first 4 days is not wasted by what I taught you today. But we wanted you to be aware that there exists this new paradigm of programming, right, that is really growing, and to be able to leverage it. So a few references that I've used in the slide. Again, each of these talks, each of these books, really brilliant. Right? I would strongly encourage number 5, the STL Algorithms in an Hour. It's a very, very nice book. Most of my DPC++ material comes from 7, 8, and 9. 7 and 8 primarily. Right? These are programming introductions from Intel. I've abstracted some of them and presented to you in a simple form that you can understand. Each of these videos is over an hour long, but they're really good. So if you're when you're going to do your assignments, that will be in DPC++. I encourage you to also look at these if you want to get more clarifications. So are there any questions right now? Any questions on anything I taught today? DPC++, compilers for parallelism, STL algorithms, STL execution sequences. Any questions so far? Okay, if not, here are your next steps. Your assignment 5 should be released soon if it's not already out. Right, this assignment will enable you to program in DPC++. Right, so we wanted you to get a handle on how it is to program DPC++. This assignment will use DevCloud so that you can run on Intel CPUs, GPUs, and FPGAs, and not Kaggle. Rupesh sent out a link to this particular YouTube video from the 24th minute to the 42nd minute. It gives you some idea of how to access and set up your jobs to run on DevCloud. I encourage you to see it. It's pretty simple. It's pretty intuitive. But this gives you some pointers towards going there. The discussion is scheduled for tomorrow morning at 9 o'clock. So please go ahead and give it a spin and come back with your questions. We'll talk about the answer to that as well. And as a reminder, we have a Ninja certificate for this particular program. Again, if you've done 3 out of 5 assignments, you get if you do 4 out of 5 assignments, you get a certificate. But if you do all 5, you get a Ninja certificate. And this is the 5th assignment for you to take first. That's pretty much it from me today. If there's any questions, I'm happy to answer them now. Are there any questions? Okay, if not, I think that's pretty much it. Thank you all very much for attending. All the best in your assignment.